This work is a joint work with Jean Blair, with Pinar Heggernes, and with Daniel Lokshtanov. And I'm going to talk about a problem concerning the maximum number of edges that a graph can have under some constraints. So the constraints that I want to put in my graph is the degree and the matching number. So one important thing to notice here is that the number of vertices is not restricted in this setting. So this means, for instance, that if I only bound the matching number and not the degree, I could have as many edges as I want, because I could have a star that has matching number 1, and I can add as many leaves as I want. And if I do the opposite thing, then I could also have as many edges as I want, because in here the degree is bounded. I have all the vertices with degree 1, but if the matching size is not bounded, then I can have as many edges as we want. So this is why we're bounding these two parameters together. And we know that bounding these two is enough for achieving a limited number of edges. We already knew that by Vizzin's theorem, that states that the edge set of every graph can be partitioned into delta plus 1 matchings. So here we are interested. So this is an upper bound on the number of edges, like a trivial one. And well, not so trivial, because the proof of Vizzin's theorem is not trivial, but a known one. And here we're interested in the precise maximum number of edges that a graph can have. So this question was actually already answered in 1976. And later on, a very constructive and combinatorial proof was given for this result, and also examples achieving the bound. So in here, just a little bit of notation that I will use throughout. By MDV, I call the graphs, the set of graphs that have degree at most d and matching number at most nu. And it's a detail that this is a strict inequality. This was already like this in the literature, so we didn't want to change. So this is the maximum number of edges, and the extremal graphs, meaning the graphs that achieve the maximum number of edges for a given degree and matching number, are actually they have the following structure. So if the upper bound on the degree is an odd number, then these graphs are just a disjoint union of cliques and stars, which sort of makes sense. And but if the upper bound is even, then we still have the stars in there. But instead of having cliques, we can do slightly better. So what we can do is the following. We start with a clique that will have an even number of vertices. And we will look at a maximum matching in this clique. We will delete this maximum matching, which is a perfect matching, actually. And then we will add one vertex that is adjacent to all but one vertex of my graph. So this will give more edges than we had before, and it will not modify the degree and the matching number of the graph. So these examples, they have a very specific structure, and actually, in some cases, they are shown to be the unique graphs achieving this, this maximum number of edges, which led to the question of how imposed properties on the graph will impact this number. For instance, we know that some sparse graph classes cannot have this many edges. And we can also see that these extremal graphs that were presented, they have, for instance, induced claws because of the stars, and they have induced C-force because of this tweaking that we did in the even clique. So we would like to know, like, if I impose this extra conditions in the graph, for instance, being claw-free or not having long induced cycles, how does this affect the maximum number of edges? So what we knew so far were results for, interestingly, the claw-free graphs and many subclasses of chordal graphs. For instance, interval graphs, unit interval graphs, and disjoint union of split graphs, and so on. And the results are quite easy, for instance, for bipartite graphs. But the question that was hanging in the air was what happens for chordographs? And that's what we do in this work. So chordographs are graphs without induced cycles of length at least 4. And they have many characterizations. You can always choose your favorite. My favorite is the one with click trees. So I will not define a click tree here, but if you're familiar with tree decompositions, a click tree is a tree decomposition of the graph in which every bag is a maximal click of the graph. And the result that we prove is the following. So we establish the bound on the number of edges that a chordograph of bounded degree and bounded matching number can have. So it's no surprise that in this case here, I don't know if you can see when I say here, but the case of the odd, this bound is the same as what we had before. Because if you recall, when for the general case, the edge extremal graphs here were already chordal, they were disjoint union of cliques and stars. But in this case here, when D is even, we have a reduction in this number of edges. And we actually show examples that achieve the bound. So for the D odd, we already had before, and now we have that a disjoint union of stars only is enough for the even. So even though the result for the odd was already known, our proof works anyways for both cases. It's not dependent on the parity of the maximum degree. And how do we prove this result? Well, what we will do is try to prove that given the bounds, we will always find an edge extremal graph for those bounds that is a disjoint union of cliques and stars. And there might be other examples. They're not always unique, but at least one edge extremal graph will be a disjoint union of cliques and stars. So I will give a slight overview of the proof, but this will be like a really not detailed overview. So if you look to the proof from really far above, what we do is the following. We start with an edge extremal graph that in some sense is closest to being what we want. This means that among all the edge extremal graphs, I choose the one that has like more connected components that are stars and also maximum number of connected components. And then I will look at a component that is not a clique nor a star. And we know this exists because, well, that's exactly our problem here. And then I will want to perform some modifications in this component in order to obtain another graph that has at least as many edges, but will contradict the closest assumption that I made in the beginning. And here, a central point of all this thing is to ensure that when I modify the graph, I don't change the matching number, I don't change the degree, and I don't destroy the chordality property. So to do that, I will make use of click trees, as I said before. And for that, I will look at a specific part of a click tree. So actually for every bag, we will look at a graph that is sort of very standard for those working with 3D compositions. This is the graph for a given bag X. I will look at all the vertices that are in the bags of the subtree rooted in X. except the vertices that are in the separator with the parent bag. So this is the subgraph of G associated with X. This is what I call Gx. And what I do now is that I process the tree bottom up, and I look for the first Gx that is not a clique. So notice that for all the leaves of my tree, the graph associated with it will be a clique. So I will look at the first one that is not. I will call this this set B, the bag, and the vertices, I will call it as a vertex set as well. And we know that this vertex set will separate the graph in two parts. One that is like the rest of the graph. And remember that the children of B have the property that the subgraph associated with them are cliques. So this set B is separating these cliques from the rest of the graph. And now I want to rearrange the edges around this set B so that things are better for me to do a case analysis in the end. For instance, a vertex in B can have neighbors in the rest of the graph, and it can have neighbors in the cliques. So I want to put some order in there. And the first thing I will do is the following. If I have a vertex in B that has a neighbor up in the rest of the graph and is not adjacent to some vertex of the cliques, then I will delete this edge, UV, and I will add the edge between V and the cliques. And similarly, I want to rearrange the edges that are between B and the cliques. So I will do a similar modification to push these edges to the CIs with smaller indices. So in all these modifications, I'm always like deleting edges and adding edges and changing the degrees of the vertices. So we really have to take care of keeping the matching number the same, keeping the degree of the graph the same, and the number of edges is clearly the same. So once we exhaustively apply these modifications, then we get a graph that has very good properties around this set B, and that we can do like a more organized case analysis that will reach a contradiction in each case. So sometimes we will be able to add an edge and obtain a graph that has more edges. Sometimes we will be able to disconnect the graph and still have the same number of edges, and therefore this contradicts the maximality of the number of connected components. So, and yeah, so that's really a case analysis in the end, which leads to the proof that there is one example that is a disjoint union of cliques and stars. And from that, it's easy to prove the bound when D is even, and which leads to the main result of our paper. And we also show that the same bound does not generalize if you, instead of forbidding the cycles that you do for chordographs, if you forbid any finite family of induced cycles. In these cases, we can always have more edges than we do in chordographs. And one such example is, for instance, if you look at C4 free graphs. Here we have this example with the Petersen graph, and with the detail that has one edge subdivided here. So this graph has maximum degree 3, matching number 5, but it has 16 edges. And the bound that we would obtain, like for chordographs, it's 15, right? So this graph, as we can see, it's triangle free, it's C4 free. So interesting open questions is to know what are the exact bounds in these cases, like in particular C4 free and triangle free graphs. And also a more like difficult question is the case of connected graphs, because here we always use in our favor the fact that we can break the graph into smaller pieces. But if you want to study this question for connected graphs, then yeah, things become a lot more tricky. Even the general case is open. Yeah, so that's an interesting question. And yeah, thank you for your attention. And if you have any questions, I'm happy to answer them.
Thank you very much, Paloma. We have a time for 1 or 2 questions maybe. So if anybody has a question, I ask you to go to the center of the room. There is a microphone there. Maybe we can try this feature now. Are you guys working with a new, maybe a new class of graphs right now?
Yeah, so now we are taking a look at this triangle free graphs and the connected graphs.
Right.
But as I said, for connected graphs, the problem becomes a lot more tricky, and
yeah,
but it's interesting.
Right. Well, I guess nobody has any more questions, so I thank you. I'm sorry we don't have any kind of clap system, but thank you very much for your talk. Everything went fine.
Yeah, thanks a lot.